Hey fellow scholars, this is Sherri Tech. This reading session presents a reinforcement learning controller for cooling systems, published by DeepMind. Heating, ventilation, and air conditioning contribute significantly to the operational cost and the global CO2 emissions. DeepMind presented a reinforcement learning approach to controlling cooling systems of several buildings that does not require a detailed and comprehensive physics-based model to be developed, resulting in 9 to 13% decrease in energy consumption. For large commercial buildings, the cooling system aims to maintain the air temperature and humidity in the building within a desired range, while providing adequate fresh air to maintain indoor air quality. The system reduces heat by rejecting heat to external environment and remove water vapor from the building. The experiments in this paper were conducted on chiller plant buildings. The water side of the system is responsible for cooling down and heating up the water so that it can be reused to cool the air. This works exactly like a refrigerator. The building temperature is impacted by sunlight, convection from outdoor air, heat from the ground, air movements, and equipment heat. These are highly variable and are challenging to the model. Normally, these are resolved using a physics model, but those typically requires modeling the building. In this paper's approach, sensors are placed across the buildings to gather real-time state of the buildings. In reinforcement learning, the system can be thought of as finite state machine. At each state, the system used the transition function to pick the best possible action that moved the system onto another state. After reaching the terminal state, the system gets the return that are calculated from discounted reward. The transition function is learned by a neural network that enables the system to pick the best possible action that maximizes the expected return. To put it into the context of this paper, the state is the array of sensor measurement containing temperature, water flow rate, equipment status information. The potential action the system can take on at each state includes turning on or off the equipment, chilled water differential pressure, number of water pumps. The full list is shown here. Once the system reached the terminal state, in this case, is the end of 5 minutes time frame. The reward is the negative total energy consumption within 5 minutes time frame around time t. The model aims to predict transition function that maximize the expected value of discounted reward. The optimization needs to satisfy several constraints. First, action values need to fall within the valid range. Second, some function of the state values is upper bounded by a predicted value. This is needed because the effects of actions on energy use can be manifested on a different time scale than their effects on some other observations. Transition function is determined by chiller plant behavior and physical environment. It is responsible for determining the best action to take. The selected actions are filtered by the building management system to ensure that only safe instructions are executed. So how is this transition function learned? It is the same as supervised learning for training neural network. The model is an ensemble of neural network for predicting action value function and observation constraint violation. The input layers here are the state-action pair. The pair is fed into shared layers for predicting mean return, and the states along is also fed into another shared layers for predicting observation constraints. Then the two shared layers are split into head layers. Each head layers are specific for each prediction. The paper showed that the system will generalize across the year, and it will improve over time as the amount of data increases. Further, the energy saving improved by 9 to 13% compared to the existing industry solution. This is a huge save and will benefit the environment at large scale. This concludes the reading session for this video. Does this get your mind going? Let me know in the comments below.